Hello everyone, my name is Anurag and I am a student of MTech from Thapar University Patiala. The co-authors of this paper are Engineer Rajesh Kumar, Dr. Shweta Goel and Sumedha. Engineer Rajesh Kumar and Shweta Goel is my guides from the MTech and Sumedha is my classmate. The title of this paper is Supplementary Cementitious Materials in Low Carbon Cementitious Binders and Concrete Composites, Fresh and Hardened Properties. So we will discuss about the introduction, motivation, and types of SCMs and the effect of these SCMs on the workability, setting time, and compressive strength. And finally, we will conclude our presentation. So as we all know that with the manufacturing of 1 ton of Portland cement clinker, it leads to the production of around 1 ton of the carbon dioxide and 0.74 kilogram of SO2, 20 kilogram of dust, and 1.15 kilogram of NOx gas. And with all these, there's a large amount of energy is required to manufacture the Portland cement because we need around 1500 degrees Celsius of the temperature for the manufacturing of cement, and for that temperature, a large energy is required. So these all are getting disturbing the environment because this amount of this carbon dioxide. Because if you talk about 1 ton of cement clinker, approximate 1 ton of the carbon dioxide is released into the environment. It is degrading the ozone layer and global warming. So what is the solution of this? First solution is that we have to stop using the cement, which is not feasible because we cannot stop using cement, and because it is a binder and it has a binding property, so we cannot use stopping it. Other solution is to reduce the clinker factor, and third solution is to use the SCMs, which are the supplementary cementitious materials. So what are the SCMs? We will discuss in the forthcoming slides. So what is the motivation of this? Motivation is that in the manufacturing of the cement, at every step there is a release of the carbon dioxide, whether it is direct or it is the indirect carbon dioxide. All the CO2 is released into the environment. It is degrading the environment and it degrading the ozone layer. So this is the motivation of the topic, that we have to reduce this CO2. So what are these SCMs? These SCMs are silica fume, fly ash, GGBFS, rice husk ash, and many more. But in this paper, I have discussed about these 4 SCMs. If we talk about the silica fume is the byproduct of the ferrosilicon industry. Specific surface area or the fineness of the silica fume lies between 18,000 to 21,500 meter square per kg, and silica range is between the 91.1 to 95.61 percentage. If we talk about fly ash is a byproduct of thermal power plant, and the specific surface area lies between 217 to 499 meter square per kg. Main oxides of fly ash are silica, Al2O3, and Fe2O3. GGBFS, which is the granulated ground brass furnace slag, it is a byproduct of the steel industry, and the specific surface area lies between 316 to 430 meters square per kg. Main oxide are calcium oxide and silica. Fourth one is rice husk ash. It is produced from the burning of rice husk, and the particle size ranges between 63.8 to 80 micron, and major oxide is the silica. So what is the effect of these SCMs on the workability? If we talk about the effect of silica fume, addition of around 10 to 15 percentage of the silica fume reduces the workability. It is due to the high specific surface area, which leads to more water demand for the hydration, so workability decreases. If you talk about fly ash, addition of up to 40% increases the workability, which is due to the less of water demand. GGBFS, addition of up to 50% of the GBFS improves the workability because of the smooth glassy surface, which creates a slip plane in the paste, and which increases the workability. If we talk about rice husk ash reduces the workability due to the high specific surface area. And coming to the setting time, silica fume increases at certain time. Lack of bleed water increase the shear distance, which eventually increase rapidly a certain time. If we talk about the fly ash, class F fly ash retards the setting time, and class C fly ash uh, increases the setting time, but not all class C fly ash. Some class C fly ash are therefore to increase rapid the setting time. If we talk about the GGBFS also increases setting time due to the slowdown of hydration of initial stage. If we talk about rice husk ash increases setting time. The activity depends on the specific surface area of the rice husk ash particles. If we talk about the compressive strength, so silica fume is responsible for the early as well as for the later age strength. It fills the pore between this concrete and between the cement particles, and it reduces the permeability because it makes the denser microstructure. Because the particle size of silica fume is quite finer than the cement particles, so it fills the pores between the cement particles and makes the structure more denser, and which is increases the strength. If we talk about fly ash decreases the early age strength and increases the later age strength. Slow polyvalent reaction due to the difficulty in dissolving glass phases. For that is the reason to which is the decrease the early age strength. And the GGBFS reduces the early age strength but increases the later age strength. Latent hydraulic properties cause the GGBFS to start hydrating when water is added. If you talk about rice husk ash increases the compressive strength due to the good filling effect and makes the microstructure more denser. So concluding it, by the use of these SCMs, it reduction in the reduce the clinker factor, and these are the better eco-friendly options than the OPC, and they makes the microstructure more denser because the particle size is more finer than the OPC, and they may be the future of the cement industry, and they enhance the properties of mortar or the concrete. So these are the references. Thank you.